All right. So I guess the first thing I want to say is remember that we have a final exam. This week is nothing but review, and the final will be on the 9th. So that's going to be exactly 1 week from today. We'll be in this room taking the final starting at 4 p.m. as usual, right? So make sure to not miss that. That's important. And then also, I promised you guys that you could turn in your any late check-in surveys that you forgot to do or any programming assignments that you didn't do. You can turn them in late for half credit up through the end of this week. This is the last week of classes. So up through the end of this week, if you get them in, I will give you half credit for that. So keep that in mind. And then, yeah, we're just going to do 2 review lectures this week, and that'll be it until the final. So, yeah, let's go on to the review slides. So feel free to stop me at any point. The review is, of course, for you guys. So you can derail me as much as you would like. Does not matter to me. But here is, let's start with some non-programming things, because I will be trying to focus at least a little bit on programming stuff. So let's see here. Yeah, non-programming stuff. First, let's talk about our ethical theories. All right. So ethics, remember, just in general, is the study of like what is right in the world. What are the good things that we should be doing? Okay. And we've had plenty of ethical dilemmas to talk about in this class. Computer science themed a lot of the time. And the first person that we talked about, a philosopher that had a good idea of how to frame this, how to study what is right, what is good, how to answer that, was Immanuel Kant was his name, and so Kant was his last name. He came up with the idea of Kantianism. That's the school of thought named after him. And his ideas, his maxims, were that you should follow that golden rule. You should act in a way that you want everyone else to always act, right? That word always was super, super important for Kant. And that means you get no special exceptions. You cannot lie or steal or cheat or anything like that. And nobody should ever do that. Even if you think you have a good reason, you don't get any special exceptions for yourself. That's kind of nice. Everybody has the same guidelines under Kantianism. And then also, you should not try to treat people as a means to an end just to get what you want, which kind of goes hand in hand with the golden rule, right? You want to treat people like people. They have their own needs, and they should be treated well. All right, so that's what Kant thought. And so you could approach any ethical dilemma under the lens of Kantianism. And so like a standard one to think about was like lying. Ask the question like, is lying good? Is lying right? Should anyone ever lie? Kant would of course say no, right? He'd ask the question, should everyone always be lying all the time? And he'd say absolutely not. So that means no one should ever lie. And that's what Kant would say. That's how he would approach the problem. All right. But of course, there are places where that breaks down. Like you'd probably want to lie to somebody who you know is going to go and murder your friend. You want to lie and say you don't know where your friend is or something. But Kant would be like, nope, sorry, we don't get that. No exceptions for us. In a perfect world under Kantianism, nobody would want to murder in the first place, I guess, is kind of the idea. And then also stealing, right? Stealing was another good example of Kantianism. Kant would ask, like, should everyone always be stealing stuff? Obviously, the answer to that is no, right? Nobody wants to be stolen from. But Kantianism, again, breaks down when you ask, like, hard questions. Like, all right, what if there's no other way to get food for your family? You're forced to steal. Is it still okay? Kant would say, no, you have to starve. So Kant would be against that because in a perfect world, nobody would ever go hungry in a sense, all right? So that's what Kantianism is all about. I guess if everybody followed his rules to the T, there would be no problems. But it does kind of break down in the real world, and we have to think about that. It's just a lens under which to view a problem, okay? So that's the goal with Kantianism. Is that making enough sense? Is it coming back to us? So yeah, just shout out if you have any questions about that stuff. The other one, the flip side of Kantianism was utilitarianism, right? We're going to just look at something based on its utility. So utilitarianism, John Stuart Mill was a big proponent of that. All of that it is we're trying to, we have some ethical dilemma in front of us. We want to decide what to do based on the amount of utility and happiness that comes from doing it one way versus the other way. Like we're going to weigh those things. We want to maximize utility, happiness, pleasure for any possible thing that we're trying to decide to do. Okay, so all about maximization, And it is like you're putting these ideas on a scale, like should people steal? Pros and cons list. You're writing a pros and cons list for everything. And again, just like Kantianism, you're weighing this over the universe all at once. Like, should I steal this piece of food right now? You're weighing the pros and cons for you, as well as like the people who you're stealing from and the rest of the world with all the butterfly effects and all that. So utilitarianism is all about you want to weigh these things, these pros and cons lists, not just for you, for everybody, all at once, for everyone, not just yourself. Legible, is it? Not just yourself. Okay, and so the idea of like you've got two things, X versus Y in utilitarianism. You make your pro-con list. All right, X is good for these reasons, Y is good for these reasons, and then okay, there's more good reasons essentially. So Y is going to be the thing I do. That's kind of how utilitarian is working. It's all about consequences as well. Like what's going to happen after I do this thing? What are all the results of it? All right. Like there's these consequences, some of them are good, some of them are bad. There's these consequences if I do it this way, some of them are good, some of them are bad. And again, it's maximize it for everybody as a whole. You, the person getting the stolen food that you're stealing, and then the person who's being stolen from all at once, right? So that's utilitarianism in a nutshell. And a good example of that is like, would you, like the trolley problem, would you flip the switch on the track and like have the train car murder just one person when it's going to be diverted away from killing 50 people, all right? That's a no-brainer for utilitarians. They'd be like, all right, yeah, that's fine. I will murder one person to save 50 people because pro and con list, 50 people are worth more than one person, essentially, okay? But you do have to be very careful about your pro and cons list. Like maybe that one person was very important. They were like a top scientist about to cure cancer or something. So utilitarianism also breaks down still, but again, it's just a good way to look at a problem, just like Kantianism. It doesn't give you the right answer. There is no right answer, as usual. But it gives you a way to approach the problem and then help you come up with your own ideas. Okay? So, yeah, that's utilitarianism versus Kantianism. Hopefully you're remembering all this stuff. Do shout out if you have any questions. And, yeah, I think I just want to keep on trucking if we're good. One last non-programming thing that I care about you remembering was fallacies, right? We had a big essay on fallacies. And all a fallacy is when you're trying to make an argument to somebody, if you mess up somehow, there's some error somewhere, that means your argument has a fallacy in it, and there's always a name too. And it does not apply anymore. That argument is wrong. Nobody can believe you. All right, so it's an error in your reasoning. It's usually during an argument. And we just had Thanksgiving, so maybe you guys have like hot issues that you guys talk about with your extended family at Thanksgiving. Fallacies run amok in those kinds of discussions, as you probably have seen. So that's funny. And every fallacy, you got to remember, every fallacy has a name. You can't just be like, all right, this argument is wrong, so it has a fallacy in it. You got to tell me which one in this class. Okay? So we learned a few ones with words and names that describe them, and you guys found some more on the internet as well. So yeah, I just want to show you some silly examples of fallacies. I found some memes that exemplify a few of the fallacies that we learned, but go back to the slides on fallacies to remember the rest of them. And then also go back to your essays, though. Here are a few memes that have to do with a few of the fallacies that we learned. So false dilemma, I think that was the first fallacy that we ever learned. So here's a silly example of the false dilemma fallacy, also known as the black and white fallacy, or false dichotomy. So the idea of a false dilemma is like you can only do thing one or thing two. Let me draw it up here. It's like you're giving the false illusion that there's only two options when in reality there's at least like a third or more. Okay, so that's what false dilemma is about. And then here's the silly meme example. Will you press the button? You get $50,000, but the person you hate the most gets $100,000. And so it's a funny meme example. Yeah, kind of showing this, right? What's implied is that, all right, if you press the button, either you get $50,000 and somebody else gets even more, and so you kind of lose the deal, or you get no money at all. Those are like your two options that it's putting in front of you, right? But in reality, like if you hate yourself, you get $150,000 all at once. So that's technically an example of the false dilemma fallacy. It's a fun meme example of that. But yeah, the second you have a fallacy in an argument, that argument is gone. That is not a valid argument anymore. Okay, so there's that. Here's a silly example about the straw man fallacy. The straw man fallacy is like you're not actually attacking your opponent's argument. You are just trying to like build up their argument in a very simple way, make it made of straw, so you can easily knock it down. You're putting words in somebody's mouth. That's what the straw man fallacy is all about. And so here's a silly example of that. Like news article, coronavirus, Austria bans all gatherings of more than 5 people. And then the meme was like, all right, if you're a family of 6, you got to shoot somebody or something like that. And so the implied thing, of course it's a joke, but like the implied idea is that like, yeah, this ban is a horrible ban. We should not be banning people. Even families, we're splitting up families. They can't be together anymore. And that is a straw man argument. I hope you understand, because it's really talking about public gatherings. Was probably what this law was dealing with. It's talking about public gatherings of more than 5 people. Families are fine. They're stuck together anyway. All right. So that's what the straw man is all about. It's like, this is not a good argument. It has nothing to do with the main problem. Okay. It's putting words in the Austrian lawmakers' mouths. It has nothing to do with the real issue. Okay. So that's straw man. And then the last one that I could find a meme for was tu quoque, which is a fun word to say. It's Latin for you too, or you also. It's trying to deflect blame by saying you did something wrong too, essentially. And then here's the silly SpongeBob example of that. And so you can still criticize somebody for something that you did wrong long ago. Tu quoque doesn't really apply. You can't just like flip back the problem to somebody and say, no, you did this bad thing too. Why are you criticizing me for it? Well, maybe you learned from doing that bad thing. All right, so that's what tu quoque is all about. It's trying to deflect blame when there should still be blame. Okay, so those are my silly examples of fallacies. Do they make sense? Do they come back to us? Yeah, just yell at me if you have any questions about this stuff. But I think what I want to go to now is Python. All right, the rest of these slides, I guess, are going to be about programming, because that was like the other half of this class, right? Very important for a computer science class that you guys remember how to program. And so I'm going to give you Python questions on the final. Just mentally prepare for that. Get your idle ready on whatever computer you're going to be taking the final on when you get here 1 week from now. And I'm going to give you Python questions. Yeah. I think you can expect to see a little bit of both. There's going to be like easy questions about just one piece of Python. I think you can expect to see that, but there might also be some combined things like, all right, do this fun stuff in Turtle Land that maybe requires some other libraries, like maybe the math library, stuff like that. So yeah, that's the kind of questions you can kind of expect to see. Simple stuff and also some more combined things. So one thing I have made for you is a cute little cheat sheet that you're of course allowed to use, because you're allowed to use the internet. So here, on this lecture 30 page, let me edit it, because like the recording doesn't really apply anymore right now. There is no recording yet. Just like don't click that link. It's like last semester's. But if you go to this page now, there is a final cheat sheet. Oh gosh, I just want to leave the page. Sorry, I released it. There is no code yet. There is no slides yet, but like you can click the final cheat sheet button. That's the one that will work right now, and that gives you a PDF with some extra cool stuff that you can use while you're taking the test. So it's just going through a bunch of Python syntax and reminding you what's happening. Like if statements, you got the before, the after, condition, and body, and like here's what happens if the condition is true, it'll run the body. If it's false, it'll run the after part. And like if else statements, they do one or the other. So I've just color coded this and drawn nice diagrams. You're welcome. All right, so feel free to look into this, if else. Stuff about loops, and then stuff about functions at the end. I'll go back to these when we have examples of them. But yeah, feel free to use this on the final exam. And let's have some examples of Python now. So I guess let's just go over the starter parts of the language, like the individual lines that make up your language. I guess the first thing that we should talk about is like variables and types. Types are very important in any programming language. So you can say like, for example, x equals 42 in Python, and that makes a variable, right? It makes a box in memory that holds on to 42, and if you say X, you will get the 42 out. Okay, you can also change what's in the box. But let's see, what's the right order, I guess, is now the question. So let's just start with that, right? And then you can print it out with the print function. So let's make a new folder for today, lecture 30 apparently. I'll go to idle. Lecture number 30. Well, somewhere on my desktop. I'll just call this Python stuff. Just a bunch of stuff all at once, all combined. So yeah, you can make variables in Python, of course, give them names, put stuff in them like x equals 42, and then you can use x instead of having to type 42 all day long. So that's really nice. So of course that's a program that just prints 42 right now. You can also, like Python knows the types of everything, like x is really, or the type of x please, x is really an integer, right? It's an int in Python land. And so remember all the different types that you get inside of Python. You've got, what are things that are ints? I drew it like a cloud, right? What's in the int cloud? What belongs there? It's whole numbers. Whole numbers are your int type stuff. You get positive numbers as well as negative numbers, but no decimals, right? If you want decimals, you got to go to the float type, all right? Float type has numbers with decimal points, okay? And you can like combine those. Obviously, you can do math stuff on integers and floats. You can add them. You can do other things. But yeah, ints look like that. And then if I made a new variable like y equals 3.14, that's a float. Okay, stuff with decimal places has is called the float type, short for floating point. Like the decimal place is included. That the point is there. All right. So let me show you some of those. What next? Also, the print function, you can give multiple things and it will comma separate the things that you give it. You can do, of course, math with integers, right? X plus 2, compute that. Compute x times 2, compute x squared and print it out. It's the double star, right? So like math works on integers and floats. And then yeah, if you want to do decimal place stuff, you got to create a float, 3.14. Could have made x a float by saying 42.0, right? Then it has a decimal secretly. So you can print y, do math stuff with y, and then it knows that there's a different type going on there as well. Like, all right, 3.14, that was a float and not an int. It was not a whole number. Okay, so those are those types. When you do conditions, you get back a bool type result. Boolean values are just numbers, or not numbers, sorry. There are things that are either true or false. So the bool type, what's in the bool cloud? There's only two things. It's a very small cloud. Capital true and capital false. And so those are the values of the bool type, and you can compute them by like comparing things. You can do comparisons. You can combine them with your and, ors, and nots. Remember how to do all that? Like those are your combinators for trues and falses. So let's go to that, and this is going to be very useful when we have if statements and while loops, right? So like you can be like B1, have that hold the result of checking if 33 is less than 34, right? This will produce, this is a true statement, so this will result in true being placed into B1, won't it? All right, I hope that makes sense. And so if I print B1, it's like, that will be true. There it goes. And then, of course, you can just hard code the values as well. Like B2, set that to false right now. That's okay as well. Like we did that for our is game over in our POM. So, of course, that also works. Print B2, just like it's already false. I don't have to do any computation, but Python's happy to do some computation to produce a bool still. There's my false right there. You can hard code it like that. And then also you can combine these things. You can be like, let's get these prints all next to each other maybe. You can combine these guys with your ands, ors, and nots. You can be like print the result of B1 anded with B2. So that's going to be true anded with false. That's going to end up being false, right? Because and is only true if they're both true. Or, though, or works and gives back true if any of them are true. including both. So B1 ORed with B2, that will be true because B1 was a true thing. So their OR is one of them or both of them true? Yes, that's still true. So go back to your truth tables if you've forgotten any of that. That's in the midterms cheat sheet, isn't it? What else? There's also not, which negates a Boolean variable or Boolean value. So there's that. What else? What else? There's strs. Strs are short for string, and strings hold a bunch of characters between quotes. So let's talk about those. So you can make a string like this in Python. Here, let me have some extra lines so this can be up top. Be like S1 equals hello world, exclamation points. That's just a string of characters, all right? And Python doesn't care about whether you use double quotes or single quotes, so both of those are strs. It's happy, like print the type of S1. It's a str all day long. It's a str there. And what can I do to it? What can you do to a string? Of course, you can print it out. You can also do operations that kind of look like mathematical operations. You can do plus and times on strs, and it acts very differently to int and float plus and times. The types are very important when you're doing those things. So, all right, let's print out S1 plus a bunch of exclamation points. So it's going to add, what it will do for strings, if you add two strs together, it will compute a bigger str, and then it'll print out all those characters. So I'm giving it to print right after that. So that's what we're going to see there. It's going to compute the bigger string, the bigger str. All right. What else can you do? You can be like print S1 times 3. You can multiply a str by an int, and it will like duplicate the str that many times. And then, of course, we're printing that out right after that. What else do I want to say? You can also figure out the length of your string. There's a built-in len function that takes a str and gives you back the size of the thing. So print for me the length of the string S1, and that tells you how many characters were in it. Apparently there's 13 characters exactly in the string. Okay? And that tells you where it ends. Like if you want to go through indices, that also will help you there. And that's a good segue into lists as well. So these are like our basic types that we get in Python for free. Are there any questions so far? Is it all coming back to us? Just shout out. This is for you guys. You can derail me as much as you want today and next time. I guess a str, you can think of a str as like a list of characters, individual characters. And lists are a bit more general in that case. What is a list? It's a way to hold a bunch of different values, potentially, in one place. Okay, so a list looks like this. You can give little not angle brackets, these are square brackets, to put the stuff that's in your list, and then that will create it. If you say L equals that will create this in memory. Like there's your L, and it's got 2, 4, 6, and 8 all together. All together like this. There's 2, there's 4, there's 6, there's 8. They're all together at once in a thing called L, and you can also access each piece of them. You can be like, all right, this is at index 0, 1, 2, and 3. There are also secret negative indices as well. You can go index -1 gives you the last thing, -2 gives you the second to last thing, -3, -4. So those are possibilities as well. Those are indices that give you, like, if I go to index 1 or index -3 of L, then I can get the number 4 out, all right? And then lists know their length, and you can also plus on lists to build bigger lists. They're very similar to strs. It's just like instead of just characters, you've got whatever, like numbers, whatever you want to put in a list. So let's do that. Let's talk about those. Let's have an example. Let's be like, all right, let's say, I'll make multiple lists. So I'll say L1 equals 5, 6, 7, 8, and 9. That's a list of a bunch of things in it, right? And I, of course, can just treat it all as one chunk, just one name for all those numbers at once. If I print out L1, there's that whole list. It has it all in one name. That's the beauty of lists. I can also go into it and get out a piece. Like if I want the 7 out, I can say print L1 at index. This is index 0, 1, 2. There's also some negative version of that, but index 2 will get me the 7 out. And I can use that syntax to also set the thing as well. Okay? So there's the 7. I can again say this. I can put it on the left side of an assignment and be like, all right, L1 at index 2, you're not 7 anymore. I'm going to make you 77. All right? And that's going to change the value at that place in the list. And like the whole list, it sees that change. If I print L1 again after I make that change, see now it goes 5, 6, 77. Like it changed the index there, and it all was there. It all got to be, it's all like propagated into L1, I guess. Yeah, so lists, they know their length. What's the len of L1? Just like for strings. There's 5 things in it, 5 different elements. Indices 0 through 4 if you use non-negative ones. And you can also add lists to build bigger lists. So here's a list L2, 1, 2, 3, 4. I can be like, all right, let's add up L2 plus L1 and then print out the resulting list. I think you can imagine what's going to be printed now. 1, 2, 3, 4, 5, 6, 77, 8, 9. Okay? So that is a list. What's that? In Python, it's called list. It's the same idea as an array from other languages, yes. Same idea as array, but Python calls them lists. Yeah, exactly. So, sadly, no, you'd have to use the range. You could do the range for that. Be like, all right, we can do that in the REPL real quick. You can say range, and it's got to be not 10, it's got to be 111 for a weird reason. And you can convert that to a list by just putting list out in front. So yeah, that's the one easy way to get that. Yeah, good questions. Yeah, it's simpler in Python. It makes it easier. Yeah, that's nice. I guess you could make, yeah, it's very helpful. No, nothing needs to be the same type. I could make a list like this. 1, 3.14, A. That's allowed in Python. It's a little disgusting if you're coming from another language, but that's totally fine as far as Python's concerned. Good questions. You can also do this. 1, 3.14, A, and then another list inside of the list. As element at index 3, like 5, 6, 7. Now you got a list inside of a list. There's the string. There's a string in there. But like if I call this L3, the thing at L of 0 is an int. No, sorry. L3 of 0 is an int. The thing at L3 of 1 is a float. The thing at L3 of 2 is a stir. The thing in L3 of 3 is another list. And then go index into that afterwards. Be like, all right, L3 of 3 is a list. Go to index 1. There's the 6. So that's a little disgusting, but possible. Length of L3 at index 0? Is that what you're saying? I think that's ill-formed because it's like, I don't know how to take the length of an int. But it knows you can ask for the length of this index because that is a type. And also the stir inside of it because len applies to strings. But yeah. Yeah. Yeah, you can check the type first. That's a good point. You can call the type function on it and compare it. Good. Yeah, that would work. Do you want to see that example? Sure, let's do that. Let's see. Let me make sure I'm not already going to do that. I'm actually going to do that example later today, so that's perfect. Remind me. I can use different types, but I have an example of using that to get a bunch of numbers until the user's done typing. So I'll show you that in just a second. Let's see. It'll take a while. It'll be the last slide today, I think. But yeah, these are great questions. Keep them coming. Let's see, what else do I want to show you on this program? Let's do an example of the input function, because that's a way to get stuff from the user. Like it's not very cool to just like hard code stuff all day long. So input is a function that takes as its argument a prompt that you want the user to see as they're typing. So you give it a little stir there, and then they'll see that as they're typing. That's kind of like asking them what you want. And then when you use input, it will return back to you the stir that the user typed. It will give you the result that the user typed on their keyboard as a string, even if the user types a number to you. Right, you're getting it back as a stir. So remember about that, and you might have to convert types because of it. All right, so let's ask the user for something. Let's be like, input. Hey user, what is your favorite number? And then I always give a space after the question mark so that like there's a spot to type. That's where the cursor is going to be placed. And then input will result in whatever the user typed. So we'll shove that into like a variable called num. All right, so after it's done, we'll shove it into num, and like you can print it back out. But remember that you're getting it as a str. It's just the characters. It's not a number. It doesn't know that it's a number yet. So my favorite number is 42. Like, there it is. It's 42, but it's 42 the str. It's really getting that back and placing that in the num right now. Okay? So remember that, because you cannot do number stuff with it right now. Like, you'll be very confused if you try to do like num times 2. Like, all right, your favorite number times 2 was, oops. Your favorite number times 2 was 4242. That's what you wanted, right? Obviously not. So what you'll do instead is you'll say, you got to convert the types. You got to say num equals, or to convert the types, you say int, the type I want, call it like a function on the thing that's like a str, and this will produce an integer version of that number if it can do the conversion properly. And then I can shove it right back into num. All right, so now num is an int. And if I print the type, that will confirm it, and it will do the right thing now with the times 2. It'll do the int times 2 rather than the str times 2. So that'll do the conversion, and now I get 84 as I wanted. Okay, so don't forget about the type conversions. That's important. But yeah, I think that's just like the basic stuff that I wanted to show you about Python. The next things that I want to show you are the ways to build more interesting programs. Let's do like if statements now. All right. So, I guess let's go to the cheat sheet. An if statement looks like one of these three options. You've got just a normal if statement that runs a body if the condition is true. So it checks the first thing that happens in an if statement. It's just by itself is it checks the condition always. If it's true, it runs your body. And then once it's done, it goes straight to the rest of the code. If the condition was false, though, it skips the body. Right? So that's what a normal if statement looks like. Remember that you got to tab over to give the body there. And it kind of lets you do this. It's like comparisons give you a way to branch, and you can do some sort of comparison to like give you a true or a false. It's like, all right, like was X less than Y? If that was true, do thing 1. Otherwise, if that was false, do thing 2. That's kind of like what if statements give you in a nutshell. And so like the basic if statement that we saw there was like if you place your condition right here, colon, press enter, idle will tab over for you properly. Just everything that's indented becomes your body. As many lines as you need to get the job done. And then that's going to get run if the condition was true and skipped if it's false. Okay, so there's that one. If else is like you want to do one thing or another. If the condition is true, run this body. Boop, go to here. Otherwise, if the condition is false, always the condition is checked first. If it's false, though, do the else body. All right, so that's the if else. And then the most general one was the if else. So you can it's like what if elif is about. You can have as many elif conditions as you want in elif bodies, as many as you need. But it's just like it's gonna go to the first condition that matches and call it a day. It's like, all right, if this one works, it'll run this body and be done with it. If otherwise, it'll try this one. So read elif as otherwise. Like if this one's true, then it runs this body and then it's done with the whole thing immediately to after. Otherwise, if none of the elifs worked, none of the conditions worked, you're going to go to the else and run that body. It's like just one of these bodies ever, though, is going to get run, and it will skip over the rest of them. The first one that works, it runs. And so that's if else. Okay? So let me give you some examples of this. So don't forget about the indentation. It should be automatic from idle, though. But let's do just a silly example of like an amusement park ride, let's say. You want to check if the user is a certain height. You must be this tall to ride the ride. So let's ask the user what their height is and check and see if it's working. Tell them they can't ride the ride if they're too short. So make a new file. I'll call it conditionals. Conditionals.py. So ask the user, hey, how tall are you? All right, so input, enter your height in inches, colon space. So first thing, remember comments look like this. Ask the user for their height. And then we want to get that in a height variable, and we're going to be doing number comparisons with it, so we might as well just immediately convert it to an int. That's totally allowable, right? Just like that. And then now I've got the height from the user, just like that. Now I can do a check. If their height was less than 4 feet or something, it's less than 48, like then you can't ride the ride or something. So like if that's true, then we want to print, sorry, you can't go on the ride. So sad. But then like otherwise, if that's not true, that means it was greater than or equal to 48. They were at least 4 feet tall, right? And then you will print something else. Remember that Python strings can be single quoted as well. Python doesn't care. It's like, all right, you can go on the ride. Happy face. So that's a good example of an if statement is going to run one body or the other depending on the result of this condition. If it's true, it'll run this part. If it's false, it'll go and skip to here. So let's say I am 42 inches tall, and it's like, sorry, you can't go on the ride. If you're exactly 48 inches, then you can go. Anything bigger than that works as well. Okay, so it's one or the other. So that's if statement. Does that make enough sense? That's an if else. Do one side or the other based on a condition. And then let's do one with elif now. Let's do a grade calculator program. So I'll get like a percentage from the user, like what's your final grade percentage, and then we'll go and do like, is it an A, is it a B, is it a C? All right, so it's going to be a bunch of elifs, and we want conditions checked in a certain order. It's like, all right, first we want to check like the hardest thing to do. We want to check if it's an A. If that's true, then we're going to print A. Otherwise, if that's false, you kind of need another comparison. Like we just know it wasn't an A. We need another comparison like, all right, was it a B? If that's true, print that as a B, be done. Otherwise, if that's false, then like, all right, now it wasn't an A, it wasn't a B, maybe it's a C. So you got to keep trying a bunch of different conditions. And so this is kind of like what the diagram for how it will execute looks when you end up doing this big long if, elif, else. It's like you're getting one side or the other. It's like, if it ever works out, if it ever is true though, you're done. Like it works out, it's done. It finds the first true one. It's kind of like what the diagram is saying. Okay, so I think it's more educational to just show you the code. So let's try that now. So let's be like, hey user, what is your grade? Input, enter your grade as a percentage, colon space. And we'll shove that into a grade variable. And then we want to do number comparisons with this. So again, we want to convert this to a number, not a str. But usually percentages include decimal places. So let's convert this to a float rather than an int. That is probably the best way to go there. And yeah, now we want to check. All right, is it an A, a B, a C, a D, an F? So all right, if the grade is greater than or equal to 90, or 90.0 if you want to be precise, then that means it's an A, right? Print A and then you're done. That's your final grade. Anything bigger than 100 is still fine, like that's your extra credit, right? So that's fine if it's an A, but otherwise, right? Elif, otherwise, we just know it's not an A. We're still not sure. Is it a B, C, D, or an F still, right? So elif, otherwise, maybe if the grade is greater than or equal to 80, there's an order to this, then it's B, right? So that's how elif is going to work. It's like, all right, otherwise, check this condition. If that's true, then print B. And you know that this is still going to be correctly checking for B's because you do this one first, right? The only way for you to get to this comparison is for this one to fail. So you know that it's less than 90, and if it's true, it's greater than 80. So between 80 and 89.999 if we ever hit the body there. Does that kind of make sense? Oh, no, you can compare it to a float. I could have said 80 here. It's happy. It doesn't matter. Let's see, but conversion is hard. Like if you do like 42.5 and you try to convert that to an int, honestly don't know what's going to happen. It might yell at you. So it's like, let's try to convert to an int the string 42.5. So yeah, it's going to yell at you if you try to do something like that. But comparisons, it's happy. It's like, all right, compare 42.5 to, is that less than 43? True. That's fine with that. But conversions, it is unhappy about, usually. Okay, it wasn't a B, elif. Otherwise, maybe the grade was greater than or equal to 70.0. Print C. So it's like you're only getting here, right, if this one failed and this one also failed. So you know it's strictly less than 80, and now if this one's true, it's between 70 and 80. Okay, so that's why it's a C. So the order is very important there, and the whole fact that like you would have stopped if it was ever true. It's like the only reason you're getting to here and trying this is if the other conditions all failed, right? And so the D comparison is very similar. Like, all right, otherwise, if that wasn't true, maybe it's greater than or equal to 60 still, and that's a D. And then otherwise, you give up, right? Else, you know it was less than 60 if that was false, right? None of them worked, so that's your F grade. Okay. So here, and your grade as a percentage would be like 95. That's an A. 65.7. That's a D, and like all the other ones work too. So I hope that makes sense. Any questions about that if else? All right. Let's do loops now. So loops, the first one that we talked about was while. It's like the most generic kind of loop. Looks very much like an if statement. It's like you got your stuff that you're coming at before. You run all this code before, of course. And then the while loop works like this. It's always going to check its condition. And if it's true, it runs its body, just like an if statement. Just like an if statement. As long as the condition's true, it will run its body. And the difference is it repeats, right? It goes back to checking the condition after the body's finished. Like, all right, maybe it's false now. It's like as long as the condition's true, it's going to keep running the body there. The second it becomes false, though, and maybe it's false at the start, we don't know. The second it becomes false, then it jumps to the rest of the code. So, for example, let's say we want to print all the numbers from 1 to 10. Let's use a while loop for that. And let's kind of break it down into this kind of diagram first before we go to code. So it's like, all right, how do we do this? We're going to need some variables. We're going to need to check some things. So I think the very first thing we need to do is like set up a variable that's like the first number we care about. All right. So that's like set I to 1. I is just our standard variable that we use. And then kind of as long as I is a value I care about printing, it's like as long as I is less than or equal to 10, as long as that's true, I'll use a loop to keep on printing I, right? Print my 1, my 2, my 3, and then increment I to make it the next round. If I just printed 1, make it 2, so that when I come back, because you always come back to your condition in a loop, as long as that's true, keep on doing that stuff, all right? And you see that's going to print. First it prints the 1, makes 1, 2, 2 is less than 10, now it prints 2. Makes it 3. It'll keep on going as long as it's less than or equal to 10. The second it gets to 11, it's like, all right, is 11 less than or equal to 10? No, false. So it stops, and then it's done. It goes to your after, whatever you have below. Potentially nothing. So there's that. So let me show that to you. Just a simple loop that prints a bunch of numbers. So I'll call this loops.py. So let's have exactly this. Be like, all right, I starts at 1, while I is a value that I care about printing. I is less than or equal to 10, if we're ascending at least. Print I, and then increment I equals I plus 1. Okay? So that's going to do that, and that's going to print from 1 to 10. There it goes. Does that make sense? That's our standard example. Something I don't think I showed us in class, but is useful knowledge, is if you ever want to stop out of a loop, you can say the word break on a line by itself. That breaks out of the loop, we say. So like if you want to stop early, and it's like it's easy to make this loop, but you for some reason want to stop early, like you hate the number 9 or something, just be like, if I is 8, and I just printed 8, or sorry, I guess if you hate the number 8, you just printed 7, you made I 8, you want to skip it and like stop early. If I is equal to 8, you can stop early by just saying break. So you just say break on a line by itself. It's a keyword, and it will stop or loop you're in right now. So it just won't continue. It'll just like bail out, escape hatch. So it only prints from 1 to 7 because of that now. That's one way to stop a loop early. Okay. Yeah, if you want an infinite loop, you just say while, and then you give something here that is always true, because it always runs when the condition is true. So you can say, the simplest thing to say is like while true, because true is always true. Yeah, that will go forever, like print high until the end of time, until you click the X on the program. Yeah, that will crash idle. We've tried that before. I didn't go over continue. You'll have to wait till CSCI 40. There's another one called continue instead of break, and it just like skips an iteration, but it keeps staying in the loop. Feel free to look into that if you're interested. I can help, but I won't test you on that. Yeah, good question. Let's see. Let's do a slightly more complicated example, I guess. Let's sum up a bunch of numbers that we get from the user, until they're done typing. And so this is going to be an example of an infinite loop, because potentially an infinite loop, because we're not sure when the user's done. So let's say that we want to sum up all the numbers that the user gives us until they type -1. -1 is just going to stand for I'm done. Like we're not going to ever like expect to see -1 as a number we want to add. I guess we have to give up a number. So we're going to give up -1. And so if the user types these numbers and then -1, we want to sum up the numbers that came before the -1. -1 just means stop. All right. Let's kind of break that down and see how it'll work. We will need break for that and an infinite loop. So that's a great segue. So all right. I want to sum up a bunch of numbers. I need to keep track of a total, right? Total will start at 0. I'll add into total. So I need to keep track of the sum in a variable. So there I am doing that. And then what? Then, well, I want to keep on getting numbers from the user until, like, they give me something that's -1. I guess there is a way to do this without a break. Maybe I'll do it without a break, just to remind us of things we already know. So I guess what I want to do, right, is get a number from the user. Like, I want to keep getting a number from the user as long as it's not -1, and like adding it in. It's like, all right, input, hey user, enter the next number or -1, colon space. And so I'll get that from the user, and I'll call that like next num equals that. And it's going to be an integer, so I'll convert it to an integer because I want to do number stuff with it, right? So I got to do that conversion. And then I guess like what I want to do is while that number is not -1, right? While next num is not equal, remember that, not equal to -1, but not the number I care about adding into my total, right? So let's say this. We want to add next num into total, and then we want to repeat the process, right? And then like get the next number. Put in the next num again, because it'll keep on checking. Like the second that's -1, it stops. So we need to keep asking for new numbers, though. That still needs to be part of the repetition, right? So add next num into total, we'll be like, all right, total equals whatever the user just typed, plus its old value. And then I want to just kind of do this all over again and get another number from the user. Do you see how that's going to repeat the process? Like, all right, add in the number they just typed, get the next number. If that wasn't -1, add it in, get the next number. If that was a -1, add that number in, get the next number. If it was -1 finally, then we stop the loop. Does that make sense? And then we'll get the total variable. Like that holds our answer now. So when we get here, next num, like the only way for this loop to stop is if next num is equal to 1. That's the only way to make this condition false, right? And false conditions stop loops. Next num must be -1, and so we'll output the sum there, and so we'll be like print. The sum was whatever was in total. So there's pretty much the program. And so let's watch it work. And we type exactly those numbers apparently. Why not? 42, 43, 44, 1, 2, 3. So I was here, like I typed 3, right? 3 was not -1. It added the 3 into the total, and now it's asking me again for a new number. I'll type -1 to mean I'm done. And then it goes back to the condition, because that finished the body. Okay, it was -1, so condition's false. I'm done with the loop. I'll continue down to here. So the sum was apparently 135 for those particular numbers. Okay, does that kind of make sense? It's going to stop whenever the user types a certain number. Okay, that's a fun one. Let's see. All right, for my last set of slides, let's do for loops. All right, for loops allow you to loop through something. We say they iterate through something, and I want you to think of that something always like a list, because you can always mostly think of it that way. All right, so like you can go through all the elements of a list L, for example. If L held like 1, 2, 3, you'll be able to go through all the values in 1, 2, 3. Range, the range function gives you back something that is for all intents and purposes a list. So think of range 50, even though it returns something slightly different. Think of it like the list 0, 1, it starts at 0 if you don't give a starting value. 0, 1, 2, all the way to 49, right? It's always less than the last number. So think of it that way. And so that's what for is going to do. I got a drawing of that. So you say for, and it's a for in loop, we say. Okay, so here is how the for loop works. You say for, give a variable name like x, and then give a list or a range, and you have a body. So all that the for loop does is like, all right, it goes through every element and calls it that variable name. So is there another element? If there is, call that variable equal to the next element, and then run the body with that in mind. And like keep running it. Keep setting that variable like x to the next element in your list or your range, and run the body with that value. Eventually you'll exhaust the list or the range and be done with it, and that's the end of the loop. All right, so this honestly makes more sense if I show it to you. So let's see, how do I want to do this? Well, let's do a couple complicated examples. All right, let's do first example. Let's find the minimum of values in a list that the user gives us. So let's get a list from the user, and then I'll show you how to find the minimum in it. So I think this was an old question, and so now I've got it. I'm finally able to answer your question. We're going to build up a list based on what the user gives us. It's going to be very, very similar to this loop, right? Get stuff from the user and like add it into a total. Instead of adding it into a total, we're going to add it into a list. So we're going to build up a list of what the user gives us. Right? That's the first thing that I want. So let's get a list first, and then we'll find the minimum out of it. So let me give a new file here. Paste. And I'll call this for loops.py, but I'll need this while loop, this one while loop to do this job here. So to build up a list is not a sum anymore. It's going to be, I want to build up a list. So I want to start from the empty list. So that's your empty list, nothing in it right now. And then while that number wasn't -1, I want to add it into the list L. So it's L, add a new element into it. So take what it was and add a new element into that list by like adding with a new list with just that element in it. That'll make the list longer, and then get the next number. So by the time this list is done, or by the time this loop is done, we got -1 from the user, and we can print the list that we built up. So here, 1, 2, 3, 42. And if I type -1, it has built up the list 1, 2, 3, -42. Isn't that nice? So it's adding it in one by one by like computing, taking the old list, which is like the 1, 2, 3, and then it's adding the next element in as a one element list, and that builds up the bigger list with that new element inside of it. Okay? Does that make sense? How that's going to build up that list for us? That's pretty cool. Which one? If I didn't have the brackets here? Oh, good question. So I think that would be a type error. It's like, I don't know how to add an int to a list. Yeah, it does not know how. Good question. So it has to be list plus list, not list plus int, sadly. All right, so that's going to build up our list, and now let's go and find the minimum of that list. And here's the secret. I think I showed it to you once upon a time, how to find like a min or a max. So let's say that this is my list. It's got like 3, 1, 2. It could be out of order. You can type it in any order, right? The idea of finding the minimum of the values in a list is that you first start with a guess. You make a guess and say like, all right, I'm going to make a guess and say that the first element of my list is the true minimum. So I'll set my variable, like my guess goes in the min variable. I'm going to say that 3, that's my current guess for what the minimum of this entire list is. And it's incorrect, but we'll update our guess, all right? And then what you do is you loop through your list and you update your guess when you find something smaller than what your current guess is. So like the next thing you'll do is like, okay, well, I guess you'll compare 3 to 3. 3 is not any smaller. You're good there. You already said that one. Then you'll visit the 1, and then you'll be like, oh, 1 versus 3, 1 is smaller, so that's a better guess for my min. So I'll set min to 1. And then you'll look at 2, compare 2 to your current guess for min. 2 versus 1, 1 smaller, we'll keep it in there. And do you see how by the time you're done with the whole list, you'll have given everybody a chance at winning out for the minimum? So that'll find the minimum for you. And so, yeah, once you finish that list, it will be correct, and we'll use a for loop for this. All right, a for loop to go through the entire list. So like for x and L, we'll say. So here's that. So step 1 is make a guess. Oops, there we go. Make a guess that the min is the first element of the list. So say, all right, my initial guess for the minimum is L of 0. That's the first thing, right? 0th index. And then I want to loop through every element of L and update our guess if we find something smaller. So for every value, call them x in L. This is what we're going to do. And so this loop works like this. It's going to set x equal to every element of that list. X will get a chance at being the 3, the 1, the 2, if that was what was in the list. And then what I'll do is, like, if x, which is the current list element I'm looking at right now, if x is a better guess for the min should be set to x. We found a better min. So we'll make sure to keep track of that. So min is, so if x is smaller than my current guess for the minimum, then x should be the minimum. Min, set it to x. That's a smaller value. And so it'll just keep getting smaller and smaller each time, essentially, that min variable, because it's always going to be compared to like whatever my current guess is, which gets better and better as we go. So by the time this loop is done, we've visited every element. X gets a chance at being every element of that list L. And so by the time the loop is finished, then min must hold, based on our ideas, right? Min holds the true min now. Beautiful. And so if I print that the min was, whatever's in min, it should be happy. So I'll do my 3, 1, 2. 3, 1, 2, -1 to create this list 3, 1, 2. And so it will update it and it will work. It finds the minimum was 1. And it'll work for any list and any jumbling of orders. Be like, all right, 8, 6, 7, 5, 3, 0, 9. It'll keep on updating as necessary. Like first 8 is the guess, then 6 is smaller, so 6 is the guess. Then 5 is the guess, then 3 is smaller, then 0 is the guess, and then that's it. All right, so it's going to work. Pretty cool. Does that example make sense? All right, I think I got one more. So for my last example, let's combine our knowledge of quantifiers and then proofs, and let's prove that this quantified statement works with code, that there exists an x such that the following is true about x. There exists a number x such that it's between 32 and 37 inclusive, and x is prime. All right, do you see how you might go searching for a value that could be x to make that proof true? So I think we just need a loop. We need a loop through these numbers and see if we find a number that's prime, essentially. That will succeed and give us our statement. All right, so let's do that. So let's be like, all right, we want to loop through, like, we just need to find one prime number that's between 32 and 37. That will prove this statement true, right? That there does exist a number. Here it is. I'll find it for you. So, all right, let's go through a range. Like for every number, call it n, let's say, in a range between 32 and 37. So I say range 32 and not 37 here, but 38. All right, let me print n to show you what's going on there. So, oops. Oh gosh, I gotta give it something. There, 1, -1. And so here's my range 32 to 37. So it's being printed out properly. So that's what n is going to range over, every number through from 32 to 37. And I just want to check and find, right, if that number, that n that I'm looking at, 32, 33, give them all a chance, see if it's prime. So I think I'll need an extra function called like isPrime to check if a number is prime. But if isPrime n gives back true, then I can print out, yeah, the statement was true. Because then I found the first number that was prime. And I can print that particular number is prime. Does that kind of make sense? So I'm going to range through these numbers and check, assume that I have this function, I'll make it in a second. Assume that I have an isPrime function. If that number n was prime, this gives back true, then that will, like, that's my x. That's my good example for x. That proves that there does exist some x between those numbers that is prime. That proves my silly little theorem there. All right? So I guess all I need now is an isPrime function. We don't have one right now. So you can look away. I'm going to teach you, or I'm going to review functions next time. It's got a def and all those things. We'll get into that. But I think I'll review that in detail next time. I'll just quickly get the job done right now. So I need an isPrime function, def isPrime. It's going to take some number, call it num. What I want to do to check for if a number is prime, like what it means for a number to be prime, right? I'm not going to test you on this, but like this is just me thinking out loud. For a number to be prime, that means that if I were to try to divide that number, like 42 is not prime, because if I try to divide it by 2, it goes in cleanly. A prime number has no factors, so I'm going to go searching for factors, right? So try every number in range between 2 and the number minus 1, essentially. Then those are the possible factors, and see if any of those works out. Like, see if that number, like 42, if you try to divide it by that number n, if it goes in clean, there's 0 remainder. So remember, the percent sign gives you back remainder. So if that answer is 0, then I will return false, because they're n, like, if num is 42 and n is 2, it'll notice that, all right, 42 divided by 2 goes in cleanly, it has remainder 0. That means it's not prime. False. It's not prime. Otherwise, though, if I try everybody, if I get out right to here, if I try everybody, and none of the numbers went in cleanly, they all didn't have a 0 remainder, that means none of them were factors of num. Those were all the possible factors, and there are no factors of n, of that original number, and so that means it was prime. True. Technically, you don't have to go this far. You just need to, if you're looking for one factor, if you look up square root on Wikipedia or something, if you look up the idea of primality checking, you just want one factor. The first factor of a number, if there is 2 factors at least, is guaranteed to be at least the square root of the number. At most the square root of the number. So I can be like, go up to not num minus 1, but go up to the square root of num. So like to the 0.5 power, round it down, and then add 1. So like go up to this number, essentially, the square root of the number. I don't have time to fully explain why that makes sense, but it's just like, it saves time. It goes to a smaller value. But that should do it. So here we go. The statement is true. It's looping, and it finds that it has to go all the way to 37, apparently. N becomes 37. 37 is apparently a prime number. That gives back true. And then it prints it out, and that proves my theorem. I think that's what I want to say. So you can just, like, don't look at this. That's beyond the scope of the class right now. But that's what I was trying to do. That code. Does that code at the bottom there make sense to us? All right. So yeah, I think that's everything that I officially wanted to go over today. Are there any questions? Because that's where I want to stop with the review. I'll go over functions next time. We'll go from there, about the turtle library and stuff like that. But is there anything out of the stuff that we talked about that you'd like me to hit harder, have more examples of? It's like, I'm here for you guys, and we have another 10 minutes. It's up to you if you think of something. Yeah, I think that's everything that I wanted to give you, at least for now. Yeah, that's a good question. So here's what I promised. I'm gonna show you what I promised here on the final info page. We're gonna stick to that. So I'm gonna give you Python questions that don't have to do with fallacies, and then I'm gonna give you an essay. So the essay might be where Kantianism, utilitarianism, fallacies come up. So it'll be in a writing question. Yeah. Yeah, I might give you potentially maybe an argument, and there might be a fallacy in that argument that I want you to find and analyze. That's totally fair game. Yeah, good question. Yeah, that's the kind of stuff you can expect to see. So here, let me stop the recording, and then we can hang out.